Bob Steneck. He is going to be, well, let me tell you where he's from. He's from the University of Maine. He is going to be talking about benthic algae and coral recruitment potential of corals or not. Benthic algae and recruitment potential of recruitment corals. That's right. And underappreciated demographic gatekeeper.
Right.
Best for last.
Thank you. And you folks all deserve a lot of credit for sticking through all this. I thank Mark and the Teasleys for putting together this really fascinating workshop and seminar. There's so much new stuff that it makes my brain hurt, and that's why I say now for something completely different. Everybody will be able to understand this stuff. The sophistication that I bring to the field is, you know, whatever I can put in a mesh bag. I'm going to start off by discussing what I call my anti-uniformitarianism theme, that the reefs of today are really not the key to the past. And the Indo-Pacific doesn't equal the Caribbean. That is, coral recruitment actually is more important now than ever before in the Caribbean. I'm also going to talk about algae as drivers of coral recruitment and describe this as a demographic bottleneck. And I'm going to talk a little bit about algal feedbacks. Mark wanted me to maybe take a little bit of a higher altitude view, and so that's sort of what I'm trying to do. We all have seen plenty of evidence that reef corals die worldwide, and 1998 actually provided a really interesting experiment, because each one of those dates was a date when corals bleached. It was the warmest year on the planet, and we had massive bleaching and bleaching death. And, you know, what you can learn from this is, you know, I've been working for a number of years in Palau, some work in the Great Barrier Reef, and a lot of work in the Caribbean. And if you look at Palau, the devastation from the 1998 event was really amazing. And when I got there in 2001, what I was seeing was very little in the way of virtually no macroalgae, a fair amount of coralline algae, and a lot of coral recruits. By 2005, the reef was looking remarkably better. 2008, and just a couple of weeks ago, Pete Mumby and I were working in Palau. These are pictures I took. Remarkable recovery, clearly a resilient reef. Now, also, working on the Great Barrier Reef, it got bleached. 2005, it looked actually pretty good after the bleaching event. Belize was an entirely different story. It was a coral reef that flipped from a coral-dominated state to an algal-dominated state, and it got locked. And so what we're seeing actually is the frequency of disturbance globally is really not all that different, but there's a real big difference in the rate of recovery, and it makes us think about these reefs in very different ways. And I'm going to start off by thinking about what's the difference between these two regions. In the Caribbean, this is a photograph I took in 1972. I was a graduate student, and I didn't have much money, so I had to do black and white. But there's a barracuda for scale. It's about a meter-long barracuda. The Acropora reefs were really remarkable. They were almost monocultures. They formed a huge amount of reef rock, and it wasn't just in St. Croix, it was all over the place. As a matter of fact, John Pandolfi and Jeremy Jackson reconstructed Pleistocene reefs, and so virtually the photograph I just showed you could have been taken in the Pleistocene. Not quite that old yet, but what's really interesting about the corals, this is a log plot, and you know, this is hyperdominance of Acropora palmata with the other acroporids. And if you harken back to the spawner and brooder information you got from Val, I'd add to that, because I've been looking at coral recruitment, you know, what corals recruited rarely and what corals recruited commonly. These were all spawners that rarely recruited, and this is when they were hyperabundant. And, you know, so these were big, long-lived corals that rarely recruited, and based on, you know, the dynamics that was looked at the time, the adaptive strategies of coral reefs were, you know, when you think about clonal biology, you start off and you're small and you grow to a larger size and you can get smaller, but what's really interesting here is as corals get bigger, their chance of getting injured increases, but their chance of dying declines. And so that's a really interesting dynamic. As a matter of fact, what they were describing there was when you got big, the mortality rate dropped to 0. This was the immortal giants of the past. And then while I was working on my PhD in St. Croix, and I was looking at Acropora palmata in the 1980s, and by 1988 and 1990, those sites had completely died. So this was the death of the immortals. It really fundamentally changed the reefs. And the modern reefs, as they're currently described, include no more hyperdominance. We have small corals. What's really interesting, if you look at them, they are primarily brooders, and they readily recruit. So that's also a very big difference. These are short-lived corals that regularly recruit. And so if you think about this kind of broadly, think about the importance of recruitment on your x-axis and your longevity on your y-axis. What we had in the past were large, long-lived corals that rarely recruited. And where we are today are really small, weedy corals. Now, on top of that, if you think about the growth rates, okay, you get so many recruits, and then, how much growth do you have? We've been doing a lot. I'm not going to talk about this particular experiment, but we set up some settlement plates in Palau. And what I wanted you to see are these 3 plates, and look at this coral. This was 2007. In 2008, this is exactly the same situation, same photograph, basically an orientation. That's 20 centimeters of growth in 1 year, linear. Now let's go to the Caribbean. Here's Acropora palmata, one of the fastest growing corals in the Caribbean. It's the dominant reef builder. And here we are over a 4-year period. And what we're talking about, in fact, is about a magnitude slower rate of growth. And so if you think about what this means in terms of coral dynamics, what we have really in the Indo-Pacific is moderate rates of recruitment, but really remarkable growth rates that can do all sorts of dynamics, like you heard from Pete Mumby, in terms of as coral grow up, the area that parrotfish can graze declines, so that in fact the bite rate per unit area increases. That's really a healthy dynamic. The coral reefs that we're looking at in the Caribbean today have a really entirely different dynamic in the sense that they recruit a little bit less than the Indo-Pacific ones. They grow a whole lot less. And so basically, coral recruitment is much more important driver of the recovery of Caribbean reefs today than certainly was the case in the Pleistocene. So that gets me to focus on what drives coral recruitment. And this is getting me to the bottlenecks in recruitment. I'd say for almost any organism that's recruiting to the benthos, you've got 3 sequential steps. You have available larvae, which is going to be a function of connectivity. You have to have successful reproduction, and then the larvae get back to the location. Then you have 2 important aspects of the habitat, which is going to be the focus of what I'm going to be talking about today. One is the propensity to settle. This is the presence or absence of settlement cues. You heard about that from Val Paul. You'll hear a little bit more. We don't really compare notes, so you're going to see some similar slides. The good part is that you could have fallen asleep and then you finally get the slide eventually. And then there's the nursery habitat, and those are the microhabitats where post-settlement mortality is low. And the reason why I point it out this way is there's been a lot of work done on connectivity. But the fact is, the game is getting to become adults. Otherwise, your fitness is 0. And so you could actually have relatively high connectivity. But if it's followed by very high post-settlement mortality, your fitness is 0. On the other hand, you can have relatively low connectivity, but in fact, if you have very low rates of mortality, you can make it. Now, I'm going to argue that actually these last 2 steps are heavily mediated by algae, very strongly driven this way. And so these are 2 photographs I took in Jamaica when I was started working there in 1978. And as you know, there was a mortality event that occurred in major grazer in this system. Diadema underwent mass mortality in 1983 and 1984, and it fundamentally changed the system. These are exactly the same location. As a matter of fact, that's the same dendrodryer colony. And in fact, this is a complete phase shift to macroalgae. So what I'm going to suggest is that there's a recruitment potential of the environment that is heavily affected by this kind of macroalgae, and I'm going to argue that algae is a key driver for recruitment. And the question is, how do we identify good drivers versus bad drivers in terms of coral recruitment? And here's the way you think about this. Good driver, hands on the wheel, looking down the road, and they have good results with very few surprises. Bad drivers. Often they have very big surprises. Examples of what these drivers, good and bad drivers can be, and I'm going to explain this a little bit more. You've heard a little bit about this. Some crustose coralline algae can induce settlement for corals, and then we have the bad macroalgae that have all kinds of hitchhikers of microbes and all kinds of things that you've been hearing a lot about. For those of you who read in ecology, you know about strong interactors, and strong interactors are processes that have a strong demographic effect, and I'm going to argue that this is one that would satisfy. I'd also suggest that the strong drivers here really should be evident at multiple scales, from millimeters to hundreds of kilometers, and it's really going to be important, and that algae are going to be the strong drivers I'm going to propose to all of you. I think if it's true that this is a very big demographic driver, then in fact it gives managers something that they can work on. And you've heard a couple of people talk about, we have a lot of global climate change concerns, but if we can manage surgically, we might be able to buy us some time. So I'm going to give you some examples of reefs that have flipped and some that have not. Many reefs in the Caribbean have flipped to macroalgae, and sometimes the macroalgal carpets are just striking. And this is some footage that Cecil V. Mumby produced. It's just simply a Belizean reef. And for those of you who are not used to looking at an algal-dominated reef, this is what it looks like. But the fact is, although some reefs in the Caribbean have flipped to macroalgae, others have not. This is Bonaire, and I've been working there for 20 years. It really has remarkably low algal biomass, and this is the last time you're going to see this illustration. But what's different about this is that whereas the Caribbean has done this, Bonaire is right about where the Caribbean was in the 1970s. With live coral cover in the order of 50 to 60%. So arguably Bonaire's reefs are relatively resilient, and they've resisted the phase shift, and in fact they are in full recovery from a hurricane that hit in 1999, and that's a very good sign, and it suggests there's not something innately within Caribbean reefs that prevent recovery, because this one is a reef that recovers. But what's really different is the real absence of macroalgae. And when you start looking at it, you start realizing that this has a lot to do with the herbivores. And you've seen illustrations like this plenty of times. Pete showed you the very nice Indo-Pacific Caribbean plot. But this is herbivore biomass versus algal biomass, or a proxy, which is the algal index. And you see the Geneva standard of a degraded reef being Jamaica. And on the other end of the spectrum, you have Bonaire with very high herbivore biomass and really very low algal biomass. This kind of relationship has been seen before. And the so what to this is that these algal carpets, they can stress corals by reducing feeding. They can smother corals. And look, we've heard plenty about all the associated problems. They can reduce the reproductive output. They can make corals more disease prone. And they can actually make reefs less receptive for settling corals, and that's really what I'm focusing on. So I've been doing this work throughout the Caribbean, and the way we look at recruitment is we put out coral settlement plates. And this is low-tech stuff, but it's terracotta plates. We leave them out typically for a year, and for most of the work that we do. And very few settlers are on the upper surfaces. As a matter of fact, this is a general case throughout the Caribbean. The sides have a modest amount, and the majority are on the undersides. The fact is, nooks and crannies are really important for coral settlement. And when you think about the major branching coral in the Caribbean, Acropora palmata and Acropora cervicornis underwent a mass mortality. We lost a huge amount of recruitment habitat when that happened. But nevertheless, if you simply look on the underside of the plates, what you see at first glance is a dog's breakfast. But when you look a little bit more closely, what you'll see, in fact, are baby corals. And, we get them at the 200 to 500 micron range, and we follow them, and in some cases we follow them for 7 years. The fact is, in some of the places, this happens to be in the Virgin Islands where we put these plates, the macroalgae was just enormous. And arguably, it actually prevents larval availability. And when we took those plates out and turned them over, they were as smooth as a snake's navel. They were absolutely without any coral or any other fouling organism after a year. But most of the plates actually did have baby corals, and we could actually look at their coordinates and we could follow these guys. And the majority of the settlers were Agaricia species and Parietes, and those are the two dominant genera that was in the Pandolfi and Jackson paper. So these are the recruits for reefs in the Caribbean today. And so we can look at these guys as soon as they settle. They're just really cute as a button, and watch them grow up. And we've been following some of these that are near the edge of a plate, and they grow up to the point where they can grow out into full sunlight, which is great. And but then we also see a lot of death, and this happens to be overgrowth by the brown alga lobophyra. And the mortality part of this is very straightforward. You've heard plenty on that. And you've also heard from Val about the work that we've been doing in collaboration, looking at aspects of spawning and settlement, because the benthos really matters as far as that goes. You have this mosaic of coralline algae. And when you take the three species that Val talked about, we see that the larvae can select those three species over some others. It induces metamorphosis and recruitment, and in fact, there's enhanced survival on certain taxa. The fact is, we know that some coral larvae are better coralline taxonomists than many reef scientists. And what about macroalgae and cyanobacteria? Again, Val went over a lot of this, but just to summarize, and this is some of Ethna Kupfer's work, we have a variety of macroalgae that can inhibit recruitment. Some of the larvae will avoid some of the macroalgae and some of the cyanobacteria, and then there's reduced survival. And for a variety of mechanisms, many of which you've just been hearing about. Well, if you think about this kind of recruitment in the garden of good and evil, any larva coming to the reef has a variety of substrates it could settle on. And if it was completely non-selective settlement, it would fall on a line of settling on everything in about the abundance that it happens upon it. So in other words, if it's above this line, in other words, what we're seeing is it's either selecting for certain substrates or mortality on that substrate is low. And that would be the facilitators. And on the other side of this coin, we have either they're being avoided or there's high mortality, and those are the inhibitors. And when we actually look at this, what we end up finding is that we have certain coralline algae and certain biofilms that are clearly the good drivers, and then we have turf algae, macroalgae, and invertebrates that are the bad drivers of the system. And so if you just simply look at the total number of spat per plate, and you look at a good driver like Titanoderma, this is one of the coralline inducers, you'll see a positive relationship. And so we have a simplified world that I'm just sort of subdividing that way, but it's a little bit more nuanced than that. If you think about connectivity, larvae come into an area, might be a quarter the size of this room, and these are coral settlement plates that are just a couple meters apart from one another, but the difference is the one on the right has damselfish, and the one on the left doesn't. And the damselfish are basically like biological cages. So without damselfish, all the parrotfish in the area, this was done in Bonaire, are able to graze, but the damselfish are so aggressive that they actually prevent parrotfish from grazing in the other treatments. So we have a paired experiment where arguably the larvae are going to be identical. But what the big difference here is that you have turf algae, not really macroalgae that's any different at all. And what we see is where there are damselfish, the turf algae, now I have an algal index here, but let me just tell you that the only difference here is turf algae goes from being 2 millimeters thick to being 4 millimeters thick. And so you see this increase in turf algae, you see a 75% reduction in coral spat, And in fact, that was on our terracotta plates. You also see a significant reduction in juvenile corals. These are just the natural corals that recruit. So it's really something where we're seeing any increase in algal biomass is causing a reduction. And we conducted an experiment where we did these inside and outside of damselfish territories. We set up cages that mimic damselfish territories. And what we found was only the area that was completely grazed and dominated by the good drivers, after a year did we have survivors. Whereas in all of the other treatments, we saw all of the cohort all drop to 0. Now that's a very big number. That we would argue that this is a very important recruitment bottleneck. All the corals die. So we wanted to test this a little bit more fully, and to test this, we wanted to look at the role of parrotfish. And we did this work in bay leaves, and this is stuff that I did with Pete Lumby and Susie Arnold. And we worked at Glover's and a carry key. And what we designed was a parrotfish exclusion device, and that's one in the control. So it looks like this. We've got the PEDs and the PED controls, and these are the naked plates. And it's another type of control, but we call them naked plates because we get more hits on our website this way. And how this works is if you just have your PED control, the parrotfish can graze wherever they want, of course, and that's pretty straightforward. The little parrotfish actually can go right through the PEDs, and they can graze as they do that, and that's fine. It's ineffective for small parrotfish. But the big parrotfish, they come and they hit these things and say, oh, okay, I can't do that, I'm just going to go around. And so what we did is we quantified the size of the parrotfish that were grazing using videos. And we did it at both places, and there are lots of little details here, but the big point I wanted to raise is that the only significant decline that we saw was among the largest sized parrotfish. It reduced turbidity just among the large sized parrotfish, not the small ones at all, in terms of the bite rates that we're seeing in the videos. We had these plates out for a year, and they were absolutely clean plates when we put them out there, and after a year you can actually look at the parrotfish bite marks around the outside. And you can use that as a year-long assay of the frequency of biting, and you can measure the size of the bites because big parrotfish would make big bites, we assume. And when you do that and you look at the bite rates, what you see is the only significant decline that the PED created in terms of bite rates was among those created by the largest parrotfish. So the PEDs reduced parrotfish grazing only from large parrotfish. And when you looked at the end of the year, what we ended up seeing was a slight difference in herbivory just for the large parrotfish, and we saw microphase shifts around these plates, but not around the adjacent ones. And this is what some of them look like. Really rather impressive algal buildup right around there. And when we look at the algal abundance, and this is an algal index, we see that the PED compared to the control and the naked plates showed a significant increase in macroalgae. And when we looked at the coral recruits, these are the ones that are just 1 year old and less, a significant decline in coral recruits. When we put all of the treatments together and we looked at the individual species of Agaricea and Coralline, these are the two big reef builders today, relative to the algal index, we see a decline in Agaricea, but more importantly, a complete decline in Coralline. So the Coralline, with any degree of algal development, actually reached 0. There was no recruitment beyond that. I would argue that's a pretty significant demographic bottleneck. And then expanding this, we did PEDs in Bonaire as well, and when you look at all of these, you end up seeing the same pattern. So what I'm trying to suggest is that this is a very major driver. It seems to be driving the major corals, and we've done this work and similar types of work looking at other systems. We worked in Honduras, and we found that if you look at coral spat relative to algal abundance, there's a significant decline. If you look at juvenile corals, not on our settlement plates, but just the little ones that are settling on the reef, we see a significant decline. And if you look at the Coralline cover, you see a positive increase, and this is along the lines of what Jen was getting at in terms of some of the value of keeping track of those sorts of statistics. We've really worked in a bunch of places throughout Mesoamerica, and when you put all of that together for juvenile corals relative to macroalgae, what you see is a very significant decline, and one could argue that this is a very bad driver indeed. So Pete and I have been very interested in what this means in terms of coral reef management. We wrote a paper on it, and it relates to sort of feedback loops that set up. And Pete gave this, we don't compare notes, and so you're going to be seeing this for at least a second time. But the kind of positive feedback that we're looking at is that when you have increased grazing intensity, it has the ability to reduce macroalgal cover. I think that's obvious in so many of the talks that we've heard today. The reduced macroalgal cover, I'm arguing, actually increases coral recruitment. The increase in coral recruitment will increase coral cover, and you certainly saw a dramatic example of that in some places like Palau. But the point is that that increased coral cover ends up focusing more of the grazing intensity because they're not grazing on the live corals, and so it reinforces that part of it. Also, the increased coral cover increases structural complexity, and you saw, I think as Jen talked about, spatial heterogeneity changes. Well, the habitat architecture drives fish recruitment, and a lot of the fish that are recruiting are parrotfish, and they're adding to this positive feedback. And the fact is that when all of these things are in place, you end up having these complex reefs. But what we're beginning to see is the fragility that can flip this system into the negative side of this whole story. And when that happens, we see the flattening of the reef that Nancy talked about, and you're locked into an unhealthy state. And one of the key things that I got out of the meeting that we've just had is that this locking is more than the simplistic way that I've just described it because, because of this, and that is we're learning a whole lot about what the consequence of increased macroalgal cover is. It's a lot more complicated, obviously, than we thought, and Mark ticked off all the possibilities, and he had to say yes to all of them. So, one of the things that actually Nancy's been going around saying, don't we have some success stories that we can talk about? You give some talks about coral reefs, and it becomes so depressing that, you give everybody the best science you possibly can give them, and then you're done, and you look up, and everybody's like looking at their sheets. God, this is terrible. I'm just going to go out and slit my throat. Well, don't, because it's really not. It's not a complete losing proposition here. There are causes for optimism. I mean, Pete showed in his modeling what you can do, but also it was touched on that there is progress in places like Jamaica, the Geneva Standard of a Degraded Reef. Sea urchins are actually coming back in places, and where they're actually coming back and increasing, it's a major grazer. It doesn't matter if it's a parrotfish or if it's a sea urchin, and you'll see, and what has Aronson and Freck show is that macroalgae decline, and corallines actually have shot up. The interesting thing is, on all the selectivity stuff that you've been hearing about, Diadema has remarkably low selectivity compared to a lot of the parrotfish. So when they come back, it doesn't matter what kind of nasty chemicals they have, they eat anything. They're kind of like I am. And so then when you think about this in terms of a phase shift, a few other people showed that these patches where macroalgae is declining, coral recruitment has increased, and there are places in Jamaica, this is very full. They're localized, but they look pretty darn good. So it's really not a hopeless case. So I'm arguing that algae is a major driver in terms of how it affects the recruitment potential of coral reef ecosystems. It's really how receptive is a coral reef to a settling recruit. It's why we can't just be managing with marine protected areas, because the coral larvae are going to be settling outside the protected area. It's the reason why we don't have baby nurseries on highways. My soapbox isn't as good as some others. And so I'm arguing that by any definition, we're looking at strong drivers that have strong demographic effects. I'd argue that we're seeing these effects from millimeters for settling corals to hundreds of kilometers, which I showed you throughout Mesoamerica. Clearly, there are good drivers and bad drivers. And so here's my management advice. Just say no to bad drivers. I talked about the underappreciated demographic gatekeeper. Well, you know, that's what happens if you don't pay attention to the gatekeeper. And so macroalgae really reduces the receptivity of coral reefs to settling and juvenile corals, and I'm seeing this across the board. I would say it's largely a result of reduced herbivory, although I do take the point that Dan and others have raised that it's not only herbivory, and there are probably interaction effects with nutrients and other things. And this supports a new paradigm on feedback loops related to alternative stable states, and Pete and I have been battling, not with each other, but seemingly the rest of the world, that there are, in fact, alternative stable states, and understanding some of these feedback loops are actually key to understanding what's at risk when a coral reef collapses, and trying to maintain and even take strong action immediately after a flip may be warranted, because the consequences of decadal or maybe half-century or longer flips is really something that I think a lot of managers would like to see. So managing herbivores that reduce algal abundance is probably the best known way to improve the recruitment potential of coral reef ecosystems. And with that, I thank you all.